Okay, we've got a good number of the people that joined. I think we'll get the session started. So I just want to say hello to everyone. Welcome. Thanks for joining and your interest in JMAG. My name is Brian Kowalczyk from PowerSys. And welcome to the session about JMAG optimization. Next, we'll hear from my colleague, Dheeraj Baba, who's one of our JMAG technical experts at PowerSys. Dheeraj is currently a senior electromagnetic design engineer at PowerSys Solutions. He's held positions as applications and project engineer focusing on low frequency electromagnetics in the past. He obtained his PhD, master's, and bachelor's degrees all in electrical engineering. His current research interests include high power density electric machine design, control, and optimization techniques, focusing on traction and aerospace applications. So let's now welcome Dheeraj to share his presentation. So take it away, Dheeraj.
Thank you, Brian. Let me share my screen here quickly. There, I hope you can see my screen. That's fine. And
yes, we can see. Looks
all
good.
Right. So thank you. Hello, welcome to this session on optimization. So this is basically a session that is created with collaboration with JSOL, which is the developer for JMAG, and the title being motor design using topology optimization and parametric optimization. So this is the overview of the session or the background for this presentation. First, I'll start with the background or the kind of motivation, and then to show the problem statement, propose few solutions, and value, go on to the value of the proposed method, and then in detail and in-depth view of what the analysis process is and the method is. Lastly, we'll have some references that I've cited this presentation. Starting with the background, typically for more focused on the EV traction machines, it is important to achieve high power density. But achieving that with the conventional experience-based designs or even improvements on the existing products may not be readily possible, or it may not really meet that exact specifications that are required. So in this sense, optimization is almost always required to meet those standards and requirements. And a design space exploration in that optimization process must be efficiently performed so as to conserve the computation resources as well as time. So then the problem is parametric optimization is something that's usually used in this scenario, but it may not always find designs that meet all the requirements. The reason being a global exploration is required, and using genetic algorithm has been proven efficient, but it's highly dependent on the variables and the ranges that are used in the parameter definition of that optimization problem. And then the second question would be, how do we perform a global exploration? How do we know it is global, or is it covering the entire design space? Also, the second problem is the computation time. Of course, there are usually massive number of designs required to perform a global exploration, and it should also, this computation time should meet the design cycle timeline in the company. In particular, if you're looking at topology optimization, that requires a lot more cases or designs to verify or make sure it explores the entire global space. So let me start with talking about these optimization methods and what is the difference between these two, the two types of methods we're looking at. So here on the left, we have the original geometry, which is defined by just some parameters. And then there's parametric optimization, where we'll usually define those parameters as a range of values. And the shape of the geometry itself remains relatively constant, but the geometry parameters are kind of modifying the position of the magnets or the holes or the steel or the barriers and so forth. And then we have topology optimization, where we define the space that is occupied by the rotor as domains, and the optimization is automatically trying to figure out which material should be where to give the best performance possible. And then let's look at the type of computation time required for these kind of optimization. First is a parametric optimization on this table. For example, the case we took here is we have 10 design variables that are pertaining to geometry, current, and current phase. And the population size is 50, and the number of generations is also 50. It's using a global search with a genetic algorithm. So the total number of cases or the designs in this particular example were 2,500. And it's possible to perform a distributed calculation, meaning the jobs can be distributed on a local network. And then there's this topology optimization. As I said, the domains are defined, not parameters. And the domains, in this case, what we call as Gaussian functions. There are 50 of those. And the population size is much higher compared to parametric optimization. It's at 200. And the number of generations is also 200. This is also using a genetic algorithm for the global search. And the number of designs or cases in this case is 40,000. And of course, this is also feasible to send down to the HPC or local network and distribute the execution. So once we talk about topology optimization, we have to address some of the challenges with it. Of course, it's a shape optimization. So based on the constraints defined, the geometry obtained from this optimization may not always be manufacturable, but it gives us a good idea of the layout of where which material should be. For example, this design here, so that's a result that is obtained from topology optimization. And we can see that there's small protrusions there that aren't exactly really manufacturable. So we have to go in and trim the geometry a little bit after the optimum design is found, and we have to make sure it is manufacturable. And during the process, we also have to make sure that changing these shapes from this to this is not impacting the objectives of the optimization. For example, if you're reducing torque ripple and this is what the design shows up, by changing this, we have to check the sensitivity of that to make sure it's not increasing the torque ripple. So here, what we're trying to do is combine these two optimizations. And both parametric and topology optimization have some advantages and disadvantages. So we can combine those and try to extract a better output throughout by using the entire optimization process. So this is what we're calling a two-step optimization process. And that's solution number one to deal with the optimization global search itself. So using the topology optimization to perform the global search, it does not rely on the designer's know-how of designing the machine or precisely defining the parameters. It will ultimately select the best layout while meeting the objective functions. And then what we can do is extract the geometry or the optimum design from that, check the sensitivities of the shapes to objective functions, and then set parameter ranges which for those small geometries such that we can do a parametric optimization and then get a better design in the end overall. And then the solution two is the introduction of a high processing computing environment, HPC. And this is where we can distribute the process. Instead of running in sequence of one after other, we can distribute all the jobs on the different nodes, and we can run them simultaneously to decrease the analysis time. So for JMAG, we have this PSL or power simulation license. A single power simulation license will allow to run 100 jobs simultaneously. So the value of this proposed method is that using the parametric optimization alone, it is difficult to reach a really high performance machine. And also it requires a lot of design know-how from the designer. So by performing the topology optimization or parametric optimization from the topology optimization outcome, it is possible to obtain a manufacturable design by manually tuning some of those shapes in the geometry. And also by combining the HPC and the power simulation license, this entire solution can be obtained in less than a day. For example, in this case, we are looking at about 40,000 designs, and on the topology optimization, approximately 10,000 designs on the parametric optimization. This just gives an idea of how the Pareto front changes by using just the parametric optimization, and the red one being the two-step optimization. So this is the baseline model that is used for this study. It's a 8-pole 48 slot machine with maximum torque of 290 Newton meters, and the magnet is a neodymium sintered magnet. And the objectives then are to optimize this such that the maximum torque is more than 350 Newton meters, and the torque ripple should be less than 10%. And of course, we are doing a 2D optimization, so it's a 2D model with a 1/8 slice, and we are using a periodic boundary there. And the overview of the analysis then is to perform the topology optimization and then perform the parametric optimization based on the optimum geometry obtained from topology optimization. And one other thing we'll do here is to define the range. After getting the results from the parametric topology optimization, we'll define the parameters and automatically find the range of those parameters using a rangefinder function. So the scenario for comparison, we did both steps. The first one is that there's only a parametric optimization, and this is for reference. And then we do the two-step optimization as described. The Gaussian functions for the rotor shape are 42, and the number of generations is 150, and the population size is 900. And then proceeding on to the parametric optimization from the result here, the dimension variables are 29 variables that describe the rotor, and the number of generations is 100, and the population size is 100. All right, I think I lost there for a quick second. There, okay. And then this is the results that are obtained from both the optimization methods. So the original geometry is highlighted here in yellow, and everything in black is the reference optimization, meaning only parametric optimization is performed. And the orange here is the two-step optimization. So we can see that the Pareto front has been improved further, and all the designs in this orange box here meet the criteria of torque greater than 350 Newton meters, and the torque ripple is less than 10%. So by adding this topology optimization and the two-step optimization process, the mean torque can be increased while keeping the torque ripple low, and we'll find a lot more designs in that by exploring the global space more efficiently. Here we're looking at two examples that are on the Pareto front for both the designs, both optimization steps, meaning one from the black and one from the orange Pareto curve. And we can see that the geometry is quite different. Specifically, the distribution of this V-shaped magnet, it's much wider here, and the flux barriers for the Q-axis is not well defined. Here we have a really good bridge shape that focuses the flux all the way in the D-axis to the stator. And looking at specific results for those two machines, we can see that the saliency of the machine is increased by the two-step optimization from 1.77 to 1.88. And looking at the torque, the parameter of both machines have the magnet torque is identical. Oh, that's wrong color here. The blue one is the magnet torque, and the one on the top is the reluctance torque. And we can see that compared to parametric only optimization, the two-step optimization produced 7.5% more reluctance torque. And here's the torque waveforms looking at, so once the final geometry is obtained, this is looking at the sensitivity of the shape of those barriers on the top magnet. These are slightly modified, and we can see that the torque ripple reduces further. So design A is the red torque waveform, and design B is the black one. So these are some things we have to manually check to make sure how the sensitivity is to changing those shapes. Sometimes we might get even better results. And also doing some structural analysis at maximum RPM of 10,000. And the results for here is about 100 megapascal is the maximum. And while the yield strength for this material is somewhere around 300 megapascal. And jumping onto the optimization time, the total time for this process was 12.5 hours, and that includes the topology optimization initially for 6.5 hours, and extracting the geometry, checking the sensitivity, and setting up the necessary process for parametric optimization is about 5 hours, and then performing the parametric optimization is 1 hour. And this is, we are talking about the two-step optimization. And just to repeat, the topology optimization has approximately 40,000 cases, and the parametric optimization was approximately 10,000 cases or designs. So give a rundown of the process again. The original geometry shape is shown here, and from topology optimization, we extracted this as the optimum design, but we can see the shapes are not well defined, and there's also no bridge at the top. So this is not manufacturable in the sense that there's nothing holding this piece of metal there. So extracting from that, it was hand-shaped to create this same shape of the air pocket and add bridges to make it more realizable or manufacturable. And then we also performed the mechanical analysis of that. And then preparing for parametric optimization, each of those shapes were defined with the 26 parameters. And here we're omitting the mesh-dependent steadiness in defining the ranges of these. And the geometry constraints are set manually, of course. And the next step was checking the sensitivity by manually changing some of the portions. And these are the results for that sensitivity analysis to identify how the net torque and the torque ripple is impacted by those changes. It can be seen here that cases sensitivities 1 and 2 greatly affect the mean torque and the torque ripple, but it also causes the magnet flux to be short-circuited when the entire portion is made out of iron. And then we performed the rangefinder analysis. So this is a function that's added, one of the newer functions that added to JMAG. Basically, you can let the rangefinder automatically run through an initial set of runs to figure out the ranges for each of the parameters. If we are doing random search, that's the amount of time it takes to determine what kind of geometries are feasible and get the optimization results. And the rangefinder function is quite efficient in determining really quickly what are the limits of the ranges of each of those constraints or parameters that are set on the geometry. And as I said, this has been recently added to version 20, and there's already been significant improvement with the version 20.1. So the black curve here is the time it took for geometry shape for genetic algorithm initial generation using the rangefinder. And version 20.1, it's quite improved. And the x-axis here is the number of geometry variables that are defined. And this is the model information for the topology optimization. Speed is 1000 RPM, the rated current being 250 amps, and the phase of the current or the current angle being 37.4 degrees. We're using 17 steps. That means 17 divisions for one cycle. And the number of mesh elements is between 12 to 13,000 elements. The speed up ratio for single core to distributed analysis, basically this plot shows that if you run the topology optimization or the parametric optimization on a single core, the amount of time, let's say, is 1. And then as we increase the number of cores, that's the speed up ratio that we get. So you can see that it kind of saturates somewhere around 40 to 50. And then this minimal increment as we increase the number of cases. By the way, to give you an idea, it takes approximately 10 seconds for the parametric optimization, each analysis or a single job, and 20 seconds for the topology optimization in this case. And this is the operating environment we were using. The number of cores we have in hand was 200. It was on a Red Hat Linux server operating system. It was an Intel Xeon Gold CPU running at 2 gigahertz and about 192 GB of RAM. And the license, we've used 2 PSL, which is the power simulation license. Estimated total job duration, of course, as I said, it was 2 PSL license, meaning 200 jobs in parallel. But this plot is just showing that it's not always necessary. With the 2 PSL, yes, we got it in close to about half a day. Even with single PSL, it should be less than a day, or even that's not available. Just with using 24 cores, it's still achievable in under 3 days, running in total of about 50,000 jobs. So that will be the end of this session, and that's the related material that I've cited here. Feel free to go and look over these. Some of these are available on the JMAG website. And there's the contact information and the website link if you'd like to take a look. And it'd be great, happy to answer any questions that you have.
So, Dheeraj, thanks for the presentation using JMAG to optimize motor designs. Great job. It was really informational. Thanks.
Thank you.
So we're now going to start the Q&A session, and to let the team know or the participants know, we're ahead of schedule, so there's plenty of time for Q&A. So if you have any questions for Dheeraj, if you could please post them on your Q&A panel, would be appreciated. So we've got a fair amount of time to answer those questions. So I'm seeing questions coming in.
Mm-hmm.
So here we go. So there are quite a few topology optimization techniques, such as SIMP, BESO, NGNet, etc. Which of these / any other is available in JMAG?
We use Gaussian functions. I think that's, if I'm not mistaken, that's the NGNet. It should be similar to that, I think. I'll have to double check on that, but sorry, I can definitely, if you contact me, I can definitely send you the links to the paper that that perfectly describes the function you're using.
So there's a few questions in this one.
Sure.
Also, is it possible for the user to implement any topology optimization algorithm in, say, Python or MATLAB?
I'm not sure about Python, but MATLAB, JMAG does link with the MATLAB optimization toolbox. And we also have, JMAG extensively supports scripting functions, so I suppose it's very possible.
Okay, thanks for the answer.
Mm-hmm.
So some more questions. Is it possible to include power factor in optimization criteria? Yes,
it can. There is a way to add an expression that calculates the power factor at the end of initial case and set that as one of the objectives as well.
Okay, great, thanks. Keep going here.
Mm-hmm.
So when comparing the parameter optimization and topology optimization, is the pole arc of V-shaped magnets changeable in parameter optimization?
Oh, sorry, go ahead.
No, and then it says from the compared two cross sections, it seems the pole arc of V-shaped magnets, a parameter optimization does not make sense.
So yeah, the first part of the answer is yes, the pole arc is a variable. The magnets can move sideways, and magnet length is also a variable. So that's the optimum design that came out of the parametric optimization. And in saying that, we also have to keep in mind that when we're defining the variable ranges, even through the range finder, there's always possibility that some combination of variables will not produce a feasible geometry at all. So we do not want to extensively constrain the range. If it's too small, probably we're not searching in the global space. But if it's too large, there's too many designs that are there's no feasible geometry for that. So it's kind of playing, it's a trade-off there. And with the defined variable range and the possible exploration space, that was one of the design on the Pareto front.
Okay, thank you.
Mm-hmm.
So still waiting for some questions to come in.
Mm-hmm.
So we'll just kind of hold for a minute here. And I've asked the attendees to go ahead and post your questions on the Q&A panel for D-Raj. Thanks. So I've got another one.
Okay.
D-Raj. Can we do a multi-objective and multi-variable optimization through JMAG, like variable more than 10?
Yeah, precisely. So that is exactly what this example is about. So here we're using torque ripple and average torque, or integral average torque, as objectives. So of course it is two, but it still satisfies the multi-objective, and you can keep adding. So you can use both torque and torque ripple, and then power factor as in variable, or maybe efficiency. So there are it can increase, but you have to keep in mind that once you increase the number of objectives, you're not looking at a single Pareto front. It's a Pareto surface now when you add 3, and you keep on adding dimensions to it. The computation resources to achieve that optimal solution increases exponentially. So it is possible. And sorry, what was the second question? Did more than 10 variables?
Oh, it said like variables more than 10.
Okay. Yeah, it is possible too. So this example uses 26 variables, if I remember correctly. So it is quite possible. But of course, again, as you keep increasing the number of variables, it is a dimension on the possible matrix of solutions. So the computation time goes up.
Okay, great. Thanks for the answer.
Mm-hmm.
So I'm getting some more questions here.
Sure.
So the examples in your presentation are 2D models.
Mm-hmm.
Can JMAG topology optimization be done for 3D models?
I suppose it can. I don't see a reason why it cannot, but I have to double check. I haven't performed that. Of course, 3D optimization requires massively huge amount of computation power. So that's not something I've checked myself. Yeah.
Okay, we'll have to look into that one.
Mm-hmm. Yes, please send me that question by email, and I'll definitely try and answer that for you.
Okay. So actually, I'm getting an actual answer from our other colleague, and the answer is yes on 3D model.
Okay, that's great.
But it, as you said, it takes a lot of resource, right?
Mm-hmm.
It's feasible, but quite a bit more resource.
Yes.
Another question is, do you know if you can run multi-physics, EM structural thermal optimization for topology optimization?
That's a very good question. I think it is possible to set it up by scripting.
Mm-hmm.
currently the optimization, the default process that's available in JMAG, like with minimal user input, is focused on single physics. It's electromagnetic or structural. But we do know that we have done similar studies with one of our technical, or a few of our technical partners on the optimization front, combining electromagnetic and structural in a single optimization. So that is possible with JMAG, but it would require a little more customization or user script to run that.
Okay, and our colleague also is chiming in that there's an example, JAC 257, that can give a multi-physics for topology optimization.
Oh, excellent.
So that's a good reference for who asked that question. So another couple more questions coming in from our Huva here is, so the first one is, what are the rules for geometry extraction from topology optimization, and why does it take so long?
The rules are, in a sense, so we are looking at the optimum geometry on the Pareto front, and then we have to determine which of those are more manufacturable, which of those shapes are more sensitive to the objective functions. Like if we change something, how drastically is that going to impact? So we have to filter through the designs to make sure, as a user, we understand which parameters we can change. And then the next part comes in is we have to define those parameters and the ranges for those efficiently, so that if we are changing the position of a line, it doesn't collide with the outer diameter, for example, or changing one line moves something else. So we have to go through scenarios to make sure the geometry is robust for setting up that parametric optimization at the second step. So that's where it takes a little time for the user to go through those steps and make sure everything is sensible for the parametric optimization.
Okay, thank you. So another question here. So is it possible to get the adjoint ADJOINT of the FEA stiffness matrix and implement sensitivity analysis using a joint method for implementing gradient-based topology optimization rather than population-based?
That is a very deep question.
Yeah. I can repeat parts of it too.
No, I think I got the main part of it. So it is possible to extract that information. Can we use that back in the optimization? That might be more of a scripting, user scripting required for it. I don't know if that's something that's readily available at the moment to just extract the information and put it back to run the gradient-based optimization there.
Okay, thanks.
But yeah, that's a good question.
So I think we have most of our questions answered. There's we've got like another minute left here. Okay, I think, Dheeraj, I think we're good. I think we're going to end the session.
Okay.
So let me just give a little bookkeeping to the attendees. So when you leave the session, you can switch to the next session in Huva, and the topic's going to be JMAG and research and development. And also, when you leave the session to start the next one, please refresh your page. So that'll help avoid any technical difficulties. So appreciate your attendance. Thanks for joining. Thanks for your interest. And Dheeraj, also, thanks to yourself for the presentation and the Q&A. So we'll end the session now. We'll let everyone go to the next session. Thanks again, and we'll talk later. Okay, bye everybody.
Bye.